So we first talked about number of signals, then chemical shift and integration values. Now there is one last piece of information that we need to know, and it's called multiplicity or J coupling. So this tells us what does this triplet mean or what does this singlet mean. So how are we going to decide what the multiplicity is? Before answering this question, let's look at the number of peaks in a signal. So if we have one peak, we call that a singlet. With two peaks, we have a doublet. With three, it's a triplet. With four, it's a quartet. And we can get all the way to seven, which we call that a septet. Now, when you get above 7, it's almost impossible to see the peaks clearly because they are so close to one another. Unless you have a very good NMR instrument, you cannot see them. So anything higher than 7, we call that a multiplet. Now we are going to determine what type of multiplicity a hydrogen will have. Now the way that we do it, we need to look at the neighboring protons. So for example, if we want to know what is the multiplicity for HA, we need to look at its neighboring proton on adjacent carbon, which is HB. So we already talked about it. Active nucleus such as hydrogen, they have a spin and they can interact with the external magnetic field. Now after this interaction, the nucleus can act as a small magnet, and it can be with the external field or against the external field. So for example, we are looking at HB right now. HB can align against the field or with the field. So if HA and HB are not chemically equivalent, meaning that they can form different signals in NMR, these alignments in HB can split the signal for HA into two peaks. So we are going to see HA as a doublet in hydrogen NMR. So, and this is happening if HA and HB have different chemical environments. So this is very important. Now there is a simple rule for defining these splitting patterns. We are going to talk about that in the following slides. So before we talk about the rule, let's look at the example that there are two protons with the same chemical environment next to the HA. So we want to know what would be the multiplicity of HA when it has two identical protons on a neighboring carbon. So what's happening here? Again, HB protons, both of them can be against the field, or both of them can be with the field, or one of them can be with the field and the other one against the field. So there could be three scenarios here. Therefore, there are three possible effects that HB protons can have on HA hydrogen, and that cause to see the HA proton as a triplet in hydrogen NMR. So basically, multiplicity talks about the influence of a neighboring hydrogen on a specific hydrogen atom. So here HB protons can influence HA, and we are going to see HA as a triplet in hydrogen NMR. Now, why in triplet the middle peak is higher than the other two? So this is just the statistics. Basically, there are two options for this scenario. However, there is only one option for each of these scenarios, which makes the ratio of the peak to be 1 to 1. So this is just the statistics that cause to see a triplet with the middle peak higher than the other two. Now that we explained what is the J coupling or multiplicity, we can use a simple rule to get to that, which we call that N+1 rule. So this rule tells us that we can look at how many neighboring hydrogens that a specific proton has, add 1 to it, and that tells us the multiplicity. So it's pretty genius. So for example, if you have one neighboring hydrogen, you need to add 1 to that, and we are going to have a doublet. With two neighboring hydrogens, you need to add 1 to it, we are going to have triplet. With 3, we are going to have quartet. So as an example, let's look at propane. First of all, how many signals do you expect to see for propane? So clearly it is labeled here. We expect to see 2 signals. So these 3 protons are exact the same as these 3 protons because there is a symmetry in this molecule. So they give 1 signal, and these 2 protons also give another signal. Now let's look at the integration for each signal. So I'm going to label them as hydrogen blue and hydrogen red. So the blue hydrogens, the integration for them so there are 6 hydrogens here that are identical, so the integration would be 6. And for the red hydrogens, we are going to have 2. Now about chemical shift. So this proton is adjacent to the carbon. That carbon doesn't have any electronegative atom next to it, so it's an alkane hydrogen. An alkane, we expect to see that between 0.9 to almost 1.7 ppm. And for red hydrogens, it's also the same scenario. It's an alkane, so we are gonna have 0.9, 1.7 ppm. Now we want to define the multiplicity. So for the multiplicity, let's look at the blue hydrogens and define the multiplicity for these hydrogens. So we need to look at the neighboring carbon and the protons attached to it. So we have 2 protons attached to the neighboring carbon. These 2 protons are chemically equivalent. So to find the multiplicity, we need to add 1 to 2, so it's 3. Therefore, we are going to see a triplet for the blue hydrogens. So that gives us a triplet. Sometimes you may see triplet is written as just a small t, so it's the same thing. Now for the red hydrogens, so we need to look at the neighboring carbon and the protons attached to them. So we have 6 hydrogens chemically equivalent. So all of them can split these 2 hydrogens. So 6 plus 1, it's 7. So we expect to see a septet for these 2 protons. Okay, so let's look at another example. We would like to define the integration, chemical shift, and multiplicity for all the protons in this structure. Now, before doing that, the first step is to define how many signals can we have in the hydrogen NMR for this structure. So if you look at the methyl groups right here, these methyl groups are interchangeable because we have free rotation about this bond. So these 3 methyl groups, they have the same chemical environments, therefore they are basically identical, and all of them together are going to give 1 signal in hydrogen NMR. So I'm going to label them as A. Now we don't have any chiral center in this molecule, so these 2 protons should be the same. So they give the second signal. And these 2 protons should be the same as well. So this hydrogen right here, this is also giving us another signal. And These methyl groups are also identical, similar to the tertiary butyl group right here. So these methyl groups are also interchangeable, so they have the same chemical environment. All right. Now let's define the integration here. So for this group right here, we have 9 protons. So the integration here should be 9. For the red protons, the integration should be 2. For the green, that one should also be 2. For the yellow, it is 1. And for the black protons, that should be 6. Now let's define the chemical shift here. So if we look at the hydrogens right here, so these hydrogens, we need to consider only one of the groups. If you define the chemical shift for one of them, that can be true for all of these. So this hydrogen is connected to the carbon, and that carbon is connected to another carbon. So there is no electronegative atoms around here. So they are alkane hydrogens. And alkane, we expect to see them 0.9 to 1.7 ppm. Now for the red hydrogens. So red hydrogens right here. So they are connected to this carbon. That carbon is connected again to 2 carbons. So again, these 2 are alkane hydrogens. So same thing, we expect to see them 0.9 to 1.7 ppm. Now for the green hydrogens, so this hydrogen is connected to the carbon, and that carbon is connected to the carbonyl group, right? So we expect to see them from 1.5 to 2.5 ppm. Now the yellow hydrogen, so this yellow hydrogen is connected to the carbon. That carbon is also close to the carbonyl group. So it should have almost the same chemical shift, 1.5 to 2.5 ppm with the green hydrogen. So both of them, yellow and green, they have a kind of similar chemical shift. Now with the black, so again, this hydrogen is connected to the carbon. That carbon is connected to the carbon. So there is no electronegative atom here. So they are alkane. And alkane, we expect to see them between 0.9 to 1.7 ppm. Now let's define multiplicity here. So again, we need to define multiplicity for one of these hydrogens, and that can be true for the rest as well. So this hydrogen is connected to the carbon. Then we need to look at the neighboring carbon, which is this carbon. So there is no proton connected to this carbon. Therefore, the multiplicity would be 0 plus 1 gives us 1. So it should be a singlet. And we show that with a small s as well. Now for the protons B. So for these protons, again, they are connected to this carbon. Now we need to look at the neighboring carbons. So on this neighboring carbon, we don't have any proton. However, on this one, we have 2 protons. So the multiplicity here should be 2 plus 1. So we expect to see a triplet for these protons. Now for the green protons, so they are connected to the carbon. Again, we need to look at the neighboring carbons. So this one doesn't have any proton. This one has 2 protons connected. So it should be again 2 plus 1. A triplet here. Now let's look at the yellow hydrogen. So this yellow hydrogen, again, it's connected to this carbon. Now we need to look at the neighboring carbons. So on the neighboring carbons, we have 6 hydrogens connected. So it should be 6 plus 1. It's a septet. And for the black hydrogens, so this hydrogen, again, we need to define the multiplicity for one of these hydrogens, and that can be true for all the 6 hydrogens. So this hydrogen is connected to the carbon, and then we need to move forward to the neighboring carbon. So to the neighboring carbon, we have 1 hydrogen attached. Therefore, the multiplicity here should be 1 plus 1. It's a doublet here. Now, there are some recognizable patterns that come up a lot in hydrogen NMR. So, for example, for ethyl group, in ethyl group we have CH2, CH3 groups connected to one another. So, if you look at the CH2 groups, the multiplicity for CH2 groups should be a quartet because there are 3 hydrogens on a neighboring carbon plus 1, so it gives a quartet right here. And for the CH3 groups, we are going to see a triplet because there are 2 hydrogens on a neighboring carbon plus 1, so it should be a triplet. Now, whenever you see a triplet with 3 hydrogens and a quartet with 2 hydrogens, you should always think about presence of ethyl group in the molecule. So that can be a missing piece in your structure. Another pattern can be tertiary butyl group. So the chicken finger, tertiary butyl, we already talked about it. All of these hydrogens are equivalent to one another. And if you look at the multiplicity for these hydrogens, so this hydrogen is connected to the carbon, that carbon is connected to the another carbon. Now on the neighboring carbon, we don't have any proton. So 0 plus 1, we should see a singlet with 9 hydrogen. So whenever you see a singlet with the integration of 9, always think about presence of tertiary butyl in your structure. So let's talk about complex splitting a little bit. So this occurs when a proton has 2 different kinds of neighboring protons with different chemical environment. So for example, in this structure, we can have 3 signals. So these 2 protons are the same, these 2 are the same, and these 3 are the same. So we can have 3 signals overall. Now let's look at the multiplicity of Hc here. So this hydrogen, Hc, is connected to this carbon, and on a neighboring carbon we have 2 protons. They have the same environment, they are the same. So 2 plus 1 gives us a triplet for Hc. So it's a triplet here. Okay. Now for Ha, so this hydrogen is connected to this carbon. On a neighboring carbon, again, we have 2 protons. So 2 plus 1, again, gives us a triplet for Ha. Now for these hydrogens, Hb hydrogens. So on the neighboring carbons, there are 2 sets of protons with different chemical environment for that. So Hb is connected to this carbon. If I move forward to the neighboring carbon, we have Hc's here. And if I move forward again to the neighboring carbon to the left, we have HA's here. So these 2 protons have different chemical environment from these 3 protons. So we cannot add up these numbers, say that we have 2 protons plus 3 protons, 5 protons plus 1, so Hb would be a sextet. So we cannot do that because these protons have different chemical environment from these protons. Now in this situation, to define the Hb multiplicity, we need to consider each set of protons separately and look at their influence on HB separately. So we are going to look at the influence of HC on HBs. So we have two HCs right here, so 2 plus 1 gives a triplet. So basically HB is split into the triplet by HC protons. And to look at the influence of HAs on HB, so 3 plus 1, we have a quartet. So HB is split into the quartet by HAs. Now, in order to define the final multiplicity for HBs, we need to combine these two together. So we can say for HBs, the multiplicity would be triplet of quartet, or sometimes we show that as TQ. So we have triplet of quartet for HB protons here. So we can have doublet of doublet, doublet of triplet, triplet of triplet. So there is a whole list of these multiplicities, but in our course we are just looking at easy complex multiplicities, I can say. So let's look at more examples to learn this concept better. Now let's look at this structure. So first of all, how many signals can we get from this structure? So there is no plane of symmetry in this molecule. We should get 1, 2, 3, 4 signals. So all of these hydrogens are different from one another. So this one gives us 1, 2, 3, and 4 signals for this compound. Now let's look at the multiplicity of each hydrogen. So for this hydrogen, this hydrogen is connected to this carbon. On a neighboring carbon, we have one hydrogen. So 1 plus 1, this hydrogen should be a doublet. Okay. Now how about blue hydrogen? So blue hydrogen, it is connected to this carbon. Now on the neighboring carbons, we have two protons that are different from one another. They have different chemical environment. So I should think about complex multiplicity. Now I need to consider this one first. So 1 plus 1 makes this a doublet. So the red hydrogen makes the blue hydrogen a doublet. And the green hydrogen also makes the blue hydrogen a doublet. 1 plus 1 is 2, so it's a doublet. So we are going to have doublet of doublet for this proton. And we show that with DD. Now how about green proton? So again, the same scenario. This hydrogen is connected to the carbon, and on the neighboring carbons we have two different protons. So we are going to see doublet of doublet for the green hydrogen as well. Now how about the yellow hydrogen? So this hydrogen is connected to the carbon. Now on the neighboring carbons, there is only one hydrogen here, so 1 plus 1 should be a doublet. So we only see a doublet for this proton. Now let's look at another example. So first of all, how many signals can you have for this compound in hydrogen NMR? So there is a plane of symmetry right here. Therefore, this hydrogen should have the same chemical environment as this one. So they are going to show one signal. And this hydrogen should have the same chemical environment as this one. So they will show another signal. So overall, we are going to see two signals for this compound. Now let's look at the multiplicity of each hydrogen. So with the red hydrogen, this hydrogen is connected to the carbon right here. Now on a neighboring carbon, we have one blue hydrogen. So 1 plus 1, we see a doublet for the red hydrogen. Now how about the multiplicity for the blue hydrogen? So this blue hydrogen is connected to this carbon. Now on a neighboring carbons, we have one red hydrogen here and another blue hydrogen on this carbon. So since blue hydrogens are exact the same, they have the same chemical environment, they cannot split one another. Therefore, we only need to consider the red hydrogen. So we have one red hydrogen, 1 plus 1. We expect to see a doublet for the blue hydrogen as well. Now, in the final exam, I'm not going to give you questions to determine the structure of compound with complex multiplicities because it's going to be challenging. You have just a few examples of these on ACE, and those examples are all that you need to know about the complex splitting or multiplicity. So let's talk about the behavior of hydroxyl proton in hydrogen NMR. So the protons bonded to carbon split each other, and due to that we are going to see multiplicities. We already talked about a few examples before. But the hydroxyl proton is not split because this proton connected to oxygen is exchangeable. So if you have an NMR solvent that has traces of water or acid in it, that can take the proton from the OH functional group through acid and base reaction, which cause unpredictable behavior for that. So OH functional group usually appears somewhere between 2 to 5 ppm. I can say in reality you can expect to see that anywhere between 1 to 6 ppm, so it's very unpredictable, and it's always a singlet which is not split. So basically, whenever you want to define the multiplicity, you should ignore presence of this OH functional group. And as I said, it has some unpredictable behavior. Sometimes instead of a singlet, a normal singlet peak, you may see that as a broad peak right here. So that little broad peak, this one, it can belong to OH functional group. So as I said, it's just very random. But when you see this peak that integrated to 1, something like this, or this one, somewhere between 1 to 6 ppm, and you're given IR and you see a broad peak in IR, you can think about presence of OH functional group in your molecule. So a lot of the times with benzene, we'll find that the peaks for these hydrogens appear somewhere between 7 to 8 ppm. So these hydrogens are directly connected to the benzene ring, and we expect to see them in this region. So they show up further downfield comparing to other protons. Now that a lot of the times we can't distinguish between these hydrogens. So there is a symmetry in this molecule. these two hydrogens have the same chemical environment, these two have the same chemical environment, and then we have this one. So we expect to see them as a separate peak. But the difference between their environment is not much. So we see their peaks appear on top of each other in hydrogen NMR. So for example, here in the more upfield region, lower ppm, we can see a triplet which is integrated to 3 hydrogen and a quartet integrated to 2 hydrogen. So if you remember, a triplet with integration of 3 along with a quartet with integration of 2, these are the sign for the presence of ethyl functional group in the molecule, and here is the ethyl group. However, these protons that appear further downfield between 7 to 8 ppm, you cannot distinguish between them because their multiplicity are very close to one another, and they are going to appear on top of each other. Another important thing about benzene is that when you see a peak for aromatic hydrogens between 6.5 to 8 ppm with integration of 5, so this number is important, you can expect to have a ring that is mono-substituted as a possible structure for that spectrum. So a mono-substituted ring is the one that one of the hydrogens is replaced by a substituent. So 5 hydrogens in the aromatic region, always think about possibility of presence of a mono-substituted ring. So we can also distinguish between compounds using hydrogen NMR. So for example, if you are in the lab and you have these 3 compounds and for some reason they are mislabeled and you need the middle one. So how do you determine which one is the middle one? If we only have IR or mass, we would not be able to determine that. They all have exact same functional groups and they have the same mass or molecular formula. So we would not be able to see any difference using IR or mass. But with NMR, we can distinguish between them. So each of these compounds are going to give us different signals in proton NMR, and that is all because of symmetry. So for example, in the first structure, we have a symmetry right here. Therefore, these 2 methyl groups are the same. We are going to see one signal for them. Blue hydrogens are the same. We see one signal for them. And yellow hydrogens are also the same. One signal for them. So overall, 3 signals for this compound in proton NMR. Now, if we move methyl over to this carbon, again, we are going to have symmetry. So we see one signal for this proton, one for methyl, one for the blue hydrogen, and one for the yellow. So we are going to see 4 signals overall. And for this compound, we are going to see 2 signals. So we can distinguish between these molecules using their hydrogen NMR spectrum.